Very warm good morning to all of you. So now we are going to start with our last day session, day 5 session on CAN course on chalcogenide based phase change memory for non-volatile data storage. So now I would request Dr. Andrew to start with his session, please.
So good morning everyone. Today we have two lectures, two topics, but first I would like to complete the lecture we have started yesterday. So there are some information I would like to show you on the crystallization kinetics and how to tailor it. So we know already we can somehow to reduce doping elements and to stabilize these AB elements in single-phase crystalline materials. But there is also another idea how to speed up crystallization and how to improve the overall performance of a phase change device. And it's based on so-called nanoscale engineering on superlattices, and the idea to produce multi-layers consisting of different type of phase change materials. In this case, we used antimony telluride and GST. As I already mentioned, antimony telluride, if you deposit it at room temperature, it's already nanocrystalline, so it has very low thermal stability, and it's difficult to stabilize amorphous phase. And the GST-124, this is typical phase change materials, the higher crystallization temperature, and it can be produced amorphous at room temperature. From the last lecture, or from this lecture, we already know that if we make the crystallization from the interface, then this crystallization proceeds much faster, because we have already some nucleation sites on the surface, and then the amorphous materials can be crystallized faster. Here, this was also the same idea to make crystalline like seeds using antimony telluride, because it's already crystalline, and then to go amorphous GST-124. Here they prepared a device with the size of 250 nanometer. There's a so-called T-shaped cell consisting of two electrodes, top and bottom. And here we also used the silicon dioxide layer for the dielectric layer, which is also used for CMOS technology. First of all, if you prepare such a multi-layer, such a superstructure consisting of antimony telluride and GST, we can find that they perform better as the homogeneous GST-124. And here, this is the dependence. This graph shows you the dependence of resistance against pulp width. And here, this is the time required to switch single phase GST-1 to full phase. So here you need 45 nanoseconds. But if you make a stack of GST and antimony telluride, you can reduce the switching times here until between 12 and 18 nanoseconds. So it improves crystallization time, switching time. This is in this case set time, and also it if you compute the power needed to this process, it's also very low. It requires like 0.60 femtojoule. Also, as I said, the idea to make this antimony telluride crystalline at room temperature and GST amorphous, it could be also confirmed by the TM measurements. Here you see some domains corresponding to antimony telluride crystalline antimony telluride, and the GST layers in the initial state they are amorphous. Here GST layers, and after the set state and set operation, these GST layers they start to crystallize. To understand this process, we can make also theoretical calculations to support this. In this case, we performed ab initio molecular dynamic simulations. For such simulations, you need first to get some idea how to create your structure. And this is one, what is good if you use TM, you know about your microstructure. You know the state of your layers, like the antimony telluride. This is crystalline, nanocrystalline, and the GST, this is amorphous. And this brings you to this idea, and then you can make such a stack consisting of crystalline antimony telluride and amorphous GST in between. Then you can also think if you this is like antimony telluride. In this case, it acts like a template for crystal growth. You can also think that if you change this template by just if you take GST instead of antimony telluride, just for comparison to see if there is some maybe differences. But now if you allow our stack to crystallize in the computer, then and we run for two different systems, we can find that the crystallization for our system for using antimony telluride template, it proceeds faster. So it requires in the computer like 80 picosecond, and if you use GST1 to 4 template, it proceeds a little bit longer, so 125 picoseconds. So now to understand why it's so, what is the reasons, you can calculate like so-called sticking coefficient. The sticking coefficient, it shows you how effectively your species can be attached to the surface or to the interface. And now if you look to the, and it's defined by this equation like Ni minus Ni divided by Ni. Ni, this is the number of impacting atoms, and this is Ni, the number of escaping atoms. So now if you look this sticking coefficient, if you calculate extracted from this IND, we can see that antimony telluride can effectively attract the GST to the surface. So the sticking coefficient in this case is like 0.1. In the case of GST template, it's much lower, so 0.01. So we called it like antimony telluride has a much thicker surface, and it can attract this GST more effectively. So, and it can enhance also nucleation rate. So also it was also demonstrated for other systems, like for tellurium titanium 2 antimony telluride, the super lattices. This is in this case the GST. It was replaced by tellurium titanium 2. This is another phase change materials. And again, in this case, the antimony telluride, they are crystalline, and also the stack made of these multi-layers, the thin layers, 5 to 3 nanometer. The performance of such stack is also nice. Also, they can perform very fast. Like I said, speed was, if you look to these heterostructures, it requires less set voltage compared to the single phase GST material. It's also pretty fast, so it needs around 8 nanoseconds for set time. and for GST already it's like 80 nanoseconds, because depending on the device geometry and materials parameter. Also, such a stack has a nice endurance, can operate to 10 to the 9 cycles, and reset voltage also, at this voltage reset time like 10 nanoseconds. So then also to understand the better performance of such a stack regarding to the single phase change materials, the authors they performed also initial molecular dynamic simulations, and they keep this layer crystalline. This is after set state, and they want to understand why this the reset is much faster, and they found that that if you heat up the system to the 1000 Kelvin, then the system starts to melt, but only the antimony telluride block melts, and these blocks titanium tellurium 2, they stay crystalline. So it shows that these layers they are more stable during the amortization process, and then they stay also crystalline for the set. So act also like a template for the crystallization. Now let us go to the summary of all the crystallization topic and how to improve it. So we started about the programming strategy. This is strategy achieved by application of programming pulse voltage to achieve the pre-structuring in the phase change device. And this pre-structure would induce faster crystallization because of shorter incubation time required for the nucleation. It shows such a PCRAM cells. It shows a nice set times less than 1 nanosecond, like 0.5 nanoseconds, and stable switching till to the 10 to the 5 cycles. Then, if you want to increase speed up crystallization of your material, you can improve it by reducing stochasticity of nucleation of the single phase change materials. Here we consider the introduction of scandium or titanium into the amorphous material, and this both compounds they generate like stabilize this ABAB units. And this, as you know, this ABAB units, they act like a nucleation sites to form the stable nucleus. So they shorten again the incubation time, and the cell PCM run based on this materials, the scandium and titanium. They showed also nice set time, like 50 nanoseconds, and high endurance here, and also for titanium it's like set time 6 nanoseconds and high endurance here. Composite can be also used. Here in this case the secondary phase is used as template for the nucleation of GST material, and the interface assisted crystal grow can be also used to speed up the crystallization. Nanoscale engineering, it's based on the formation of superlattices, and I showed you 2 examples. One is based on antimony telluride titanium tellurium 2, and it shows a nice cycling endurance here, and short set time of 10 nanoseconds. This was partial type cell, and for germanium telluride, antimony telluride superlattice also we have seen yesterday one example. It also shows like 50 nanosecond set times and high cycle endurance. So overall, doped and superlattice like PCM devices show better performance compared to single-phase GST cells, including low power consumption, faster switching times, better endurance, and lower resistance drift. So that's all what I want to say to the crystallization kinetics of phase change materials. Now we will move to the topic of lecture today. So, and here we start the proceed further with materials engineering for device performance optimization. We already have seen some data how to optimize the devices like doping, superlattice structure formation. But here I would like to give you some more information on this topic, and we will consider in this focus on the optimization of GST-225 and germanium telluride thin films. And here we will consider the doping induced by two types of elements, the group of elements by the P block elements. This is carbon, nitrogen, oxygen, and silicon. These elements are widely used by microelectronic industry, and this is standard doping elements. So it's also interesting to see how these doping elements behave inside of GST material. Also some transition metals, scandium, we have already seen titanium, also chromium, we will consider, and there are also a huge number of other elements, but I will not consider it in this topic today, but there are many experimental data in this direction. Also post-transition metals like aluminum, zinc, gallium, silver, indium, tin, and bismuth, but I will consider only one from this group, and alkaline earth metals. I will not look to the data. Also, you can make material optimization by creating so-called germanium and GST alloys, or you can make a composite like oxide GST. For example, I will consider zinc oxide, titanium oxide, also silicon oxide. We know some data on this. And in all cases, the strategy of this topic for material optimization by composite formation, they aim to increase TC, so to stabilize the amorphous phase of GST materials, which is still an issue, and also to modify the structure of the amorphous state to enhance the thermal stability and then data retention, which is still an issue. In addition, the composite alloys like oxide, like SiO2 or titanium oxide or tantalum oxide, they can also reduce the thermal conductivity of PCM devices, and this will help to reduce the heat and dissipation, and so it will improve the reset current. Also alloy of GST, these single elements oxide materials can increase the initial resistance state of amorphous phase, and this will help also essential in the reduction of rated current of PCM. So again, we have effect of Joule heating, and if we have high resistant phase, amorphous phase, we can effectively melt it because of this high resistance of amorphous phase. Also, it's also an advantage to have a crystalline, high resistant crystalline phase, because then it will also reduce the reset current. This is just like considerations, like ideas, what you can do or what you can improve with these doping elements. So now some terminology, what is doping and what is alloying, and how they can be separated, distinguished one from each other. So doping, as I said, this is the widely used element in microelectronic industry, and it's aimed to change material properties and microstructure. Alloying, this is the formation of solid solution of two or more elements, one of each is metal. This is like germanium, antimony telluride, this is alloy. Now let us consider difference between doping and alloying, because in the literature it's always mixed. So doping, this is if you have introduced impurities to your material in very low concentration range, like in this concentration range, 10 to the -7 atomic percent, it's very low. It's used for the semiconductor industry. Then we are talking about doping. And the second criteria, that the doping does not change the crystal structure of the host material. This is the two criteria how to define the doping. Now if we follow this terminology, so if we go more than this atomic percent, more than 10 to the -7, then we are talking about alloy. However, in the case of the GST material, we know already that it contains around 20% of vacancies. And if these doping elements go from these vacant sites, then we can talk also about doping. But if these doping elements, if they not change the structure, then we are talking about doping. In all other cases, we will talk about alloying. So if you introduce several percent of impurities into your material, this is already like alloy, because the impurities, they will take some sites in your material, and then it's already not doping. This is more like alloying. However, if they introduce the doping elements and if they have a formation of additional phase, then we will talk about the composite. If we introduce oxide, then we have composite material. But as I said, in many papers they talk about like doping with oxide of GST, which is wrong from my opinion. So. Now let us look how can we consider, how can we introduce the doping elements into the materials. We can use magnetron sputtering. Yesterday you had a tutorial on this method, and you also have seen how does it work. And here, how to make the doping. You can make very simple way to dope your elements in each sputtering system. Like you have some residual pressure of oxygen, or you can also introduce some gases into the system, and then during the sputtering of GST material, you can internally introduce either argon, nitrogen, or oxygen, and then you can introduce the doping into your material, like nitrogen or oxygen, which is also depend on the flow rates and other parameters. You can also use co-sputtering of phase change target and another target like carbon target or different targets. Then you get also get some materials inside, some impurities inside of your phase change materials. During like other methods, PLD, you can use the one single target, or you can also introduce some gases in your system, then you get also doping. During MBE, you achieve like co-deposition of different dopant atoms, and also very widely used method. This is the ion implantation. We consider this, and here you can use different ions to to dope or to insert these impurities, doping elements into your phase change materials. So now let us look to the change of parameters. In the case if we use nitrogen doping, if we introduce it to the GST 225. Here, if we introduce this element to the GST material, then it influences crystallization temperature, so it increases a lot. Just think about the TC of GST 225, it's around 160 degrees C. It's also increased the energy for crystallization. This is like 3.6 against 2.4 for undoped. So overall, this nitrogen doping increases the thermal stability of the amorphous phase. It also changes the initial resistance of doped material. So if you introduce 12% or 7% of nitrogen into GST, then we get like we see the more than 2 orders or between 1 or 2 orders of magnitude of resistance change, which, as I said, it's good for reset operation. Then also microstructure is also changing. If you introduce the nitrogen the dopant, then the grain size of your material, crystalline materials, is reducing a lot, and so it also influences the endurance of your phase change devices. Now, if you want to understand why is your material thermal stability is increasing, so you can apply XPS. This is X-ray X-ray spectroscopy, X-ray photoelectron spectroscopy, and here you can study the bonding in your sample. So we know in amorphous materials you have germanium, antimony elements, and it's interesting to know how these impurities, how they bond to each material. And here the nitrogen, it makes bonds with germanium, and this stabilizes the amorphous phase, because to break such bonds there seems to be stronger as a normal germanium telluride, antimony telluride bonds which present in the amorphous state. So you see here increase of TC a lot. So now let us look also some material parameter and also some device performance. So increase of TC we know already, and energy for crystallization, so it shows high thermal stability. Although some different publications shows little bit different results, but overall this is huge improvement of crystallization temperature. But nitrogen is also lower the melting temperature. So for standard GST 225, it's like 620 degrees C, and the doping with 3.5 atomic percent of nitrogen, it lowers the melting temperature to 600 degrees C. And this is also advantages if we want to reset our cell, because we can effectively amorphize this material. And also it affects the thermal conductivity. The thermal conductivity of amorphous phases also decreases from 0.3 to 0.2, which is also good. So it's for electrical memory we need also high endurance. It also improved this particular nitrogen concentration, like at around 4%. It improves from undoped to doped. This is one other improvement, one other magnitude of improvement. However, unfortunately, phase change devices based on doped GST, they are not so good. They perform nicely, like they have reset voltage on the average of 3.3 volt. for requirement for CMOS integrity should be a little bit more, but it has nice reset times, like in the range 50 to 100 nanoseconds, but the retention time of such a cell and endurance also, as I said, can be improved here, because it's like between 10 to the 7, 10 to the 9. For the CMOS integrity, we need to the 6 and don't shows like also on this range, but it's a little bit better. But the problem here is the retention time. And the retention time is very low, like it's 2 years at 85 degrees C, and the microelectronic industry requires like at least 10 years at 100 degrees C, or like at 90 degrees C, at 90 degrees C, yes. So overall, nice topic. It improves a lot of your phase change material, but somehow the retention time is not good. Maybe can be improved by other doping. So now let us consider the nitrogen doping in germanium telluride. It also increases TC, the crystallization temperature, and also resistance. So the increase of TC is also very huge, like almost 98 degrees C. This is for pure, this is for nitrogen doped. And also the increase of resistance is also around of 1 order of magnitude for this nitrogen concentration of around 10%. Set and reset voltages, they are like also lower compared to the pure germanium, compared to the GST225, but they introduce like a reverse effect, they somehow larger than for pure germanium chloride. But this higher resistance of G cell, it makes the operation of the cell much more efficient. So the endurance characteristics, it's also large, 10 to the 5 cycles, but it's not large enough for the application. But it has high data retention temperature, like 241 degrees C for 10 years, which is for GST, it's 90 degrees C for 10 years. So this materials, nitrogen doped germanium telluride, seems to be very promising materials, and maybe we need to make more research in this direction. Now to the oxygen doping. Oxygen doping also increases the transition temperature, crystallization temperature of amorphous GST. If you introduce like 30% of doping, you can increase it to 192. But if it's less, it's like on the average of pure GST, a little bit higher, but on this average. It also increased, so overall thermal stability. It decreases a little bit the melting temperature, which will affect the power consumption. But the problem here is the precipitation of secondary phase, like antimony telluride. If the doping of nitrogen in GST exceeds this value, like 20 and 30%, and the GST and the GST alcohol is like between 10 and 15%, and then you have already some precipitates. So also nitrogen oxygen doping impacts the overall resistance. It increases by more than 1 order of magnitude. And also here to understand the high thermal stability of this GST with oxygen, we can make express measurements, and we can see the formation of germanium oxide bonds. And this also explains why this amorphous phase is stable, because for crystallization you need to break these bonds. And also there are some data on performance of PCM devices based on this oxygen doped GST material. Here, they are summarized in this table, and you can see that all data, all performances of such cell is in the green area. So also as required by the CMOS integrity, it was compared for real devices with 180 bottom electrode size. This is so-called 13 micrometer CMOS technology. And you can see that the reset times is like on the same average. Reset voltage, also current, endurance even larger, and retention time also resistance ratio even better as required by the CMOS technology. So it seems to be it's very nice material for oxygen. It's very effective for doping of GST. The problem with such data that you cannot find how much oxygen they introduced to the GST, because it's mainly done by the companies, and they never say you how they prepared this material. And this is the huge problem. But anyway, what I know from the companies, by private talks, discussions, or also you will find in the literature that the GST is never used as a single phase material. They introduce some doping to the material. Also, they never say which type of doping, but here I can speculate that maybe they introduce oxygen because there's a standard doping elements in the microelectronic industry. So, but nevertheless, there is also another materials like carbon doping. This year there was also one publication on the topic of GST with carbon. They showed very nice performance of the cells, with high endurance, low switching currents. And here let us look to the some basics what carbon makes to the material from the basic research side. So it's such doping. It also increases TC to even to the 340 degrees C. If you introduce 10% of carbon doping, and also it increases accordingly the data retention till 130 degrees C for 10 years. Reset current, however, for such cells, if you make a cell based on this, then for pure germanium telluride, it's measured like 100 nanoseconds in this publication. And if you make a doping, the reset currents, unfortunately, set currents, unfortunately, is 2 to 5 times longer. But the carbon germanium telluride, it yields about 30% of reset current reduction compared to the pure GST germanium telluride. Also, to understand these properties like of high thermal stability, you can study again, perform some measurements on the bonding, how the carbon bonds to the elements in the germanium telluride. In this case, interestingly, not surprisingly, that germanium bonds to carbon bonds to germanium, but surprisingly, there are some carbon-carbon bonds, which also suggest the precipitation of such germanium carbon type phase, and some such phase can form the clusters, and the breaking of such CC bonds. This is extremely endomatic process, and long chains could be obstacle for the crystallization of the amorphous germanium telluride. So maybe doping with carbon of germanium telluride is also from one side it will improve the thermal stability, but from another side it can bring some issue for the crystallization of this material. Now let's look at the carbon doping of GST 225. So the carbon doping, again, it increases the TC of the material for such huge temperature, like a double, with only small amount of of carbon, 3.5 atomic percent. It also affects the set and reset state, set and reset characteristics, like it reduces reset by the values like a double, it's less than for pure it's 1 dBA, for doped this is 0.5, and set is also achieved at low current. And so this brings again to the low power consumption, and also the resistance drift was also better than of GST 225, but somehow the operation speed was not good compared to the pure GST, but it increases the endurance of the GST 225 to the 10 to the 8 cycles. For GST 225 it's like between 10 to the 6 and 10 to the 7. And this is one of the main reasons why the industry introduced several topic elements to the GST materials to increase this endurance. From the structural sides, if you introduce carbon to the GST, atomic tomography, it shows the formation of germanium, the carbon bonds, antimony carbon bonds, and tellurium carbon bonds, also such as germanium carbon clusters in the film with topic 3.5 atomic percent. But these carbon-based bonds, they break on the heat, and if they heat up the system, they can be broken, and then carbon atoms form like nanometer-sized carbon clusters in CGST. At IMD, ab initio molecular dynamic simulations, they suggest that there is some reduced crystal growth velocity near carbon atom, especially at the carbon clusters, and can explain the operation speed of such CGST cells. Also, carbon impacts the population of AB rings in amorphous CGST, and it increases the number of homopolar bonds, which are responsible for this high thermal stability, also in addition to these carbon bonds. So here we can see that although we can suppress the formation of such AB rings, the operation speed of such cell is not good, even less than for pure GST. So now to the zinc doping of GST 225. So from experimental results, again, it also influenced GC crystallization temperature and resistance of this phase. So GC can be increased up to 272 degrees C. 10 years data retention can be also increased. XPS, it shows the formation of zinc antimony and zinc tellurium bonds, explaining the high thermal stability of amorphous phase. And also some optical measurements, they showed increasing of band cap for doped zinc doped amorphous thin films is the increase of like 0.1 eV. Also, ab initio IMD simulations showed that the number of these AB rings, photo rings for zinc top materials, it reduces. So the number reduces, but there is increase the average number of homopolar core, like germanium, antimony, and germanium-antimony bonds. And these top ones are mainly bonds to the tellurium. It's confirmed by the XPS, but also they found some zinc antimony bonds. And this all structural data, they also explain why this amorphous phase is stable. One is the reduction of these four-fold AB rings, and the formation of homolar chrome bonds in this material. Now to chrome doping, it's non-standard as it seems. There are non-standard elements, but again here the TC is increased a lot for pure GST. Data retention is also increased by the double. EC is also increased for chromium doped GST. The performance of such, the Express showed also the formation of bond, chromium germanium, chromium antimony, the chromium telluride bond, which also can explain the thermal stability of such compound. The performance of such PCM cell based on these materials, it was also measured, and the set voltage was achieved like with pulse width between 30 and 500 nanoseconds, but endurance in this case was not so large as we want. But high TC, but low endurance and high switching voltage make like chromium GST for some maybe special applications. Now titanium doping to GST 225. Here again there is an increase in the crystallization temperature till 230 degrees C, increase of data retention, also reduction of resistance in amorphous state for titanium doped GST, but also they found the increase of resistance in crystalline state. From the microstructure, introduction of titanium to the GST, it affects the microstructure, so it reduces the grain sizes of crystalline phase. Here, this is the GST with typical grain size between 10 and 20 nanometers. And here the grain sizes of such top materials can be reduced until 10 nanometers like here. The performance of cells based on these materials was also measured. So the reset time was on the average of 100 nanoseconds, and as for pure GST, but the reset voltage was reduced like by a double from 3.5 to 1.75. Endurance unfortunately was not so high as we want. The normal value for the application we need at least 10 to the 7 cycles if you want to apply such material to the device and if you want to produce a product from that. So now also one interesting material, this is like germanium rich GST material. This material, why it's let's say was tested, because the germanium rich materials, they can improve the thermal stability, overall thermal stability of this GST alloy. So the rich phases, they are located like in this part of the tellurium antimony germanium rich diagram. You can find different composition of this germanium rich material ranging between 212 to 161. But the industry or some research groups, they found one golden composition. This is like germanium 2 antimony 1 tellurium 2. And why do we need these materials with high thermal stability? If you want to apply them for automotive applications, we need that such materials can also they should have like crystallization temperature in the range of 260 degrees C, and they also the data retention should be also much larger than for the pure germanium GST alloy. And so there was a research in this direction to improve the thermal stability of the GST. So you see here, if you make a soldering process during device production, you apply here the temperature like 2 minutes, so at 260 degrees C. For this golden composition 1212, it was found that the crystallization temperature increases a lot to 250 degrees C. For pure, this is like in this range 150, 160. Also, this composition, germanium rich GST, shows higher resistance in the crystalline state than in GST 225. This also helped to reduce the reset current. There were also some tests on device performance of such composition. You can see it was tested by ABM, that we created a chip with memories density 128 megabit. And here they tested different devices with bottom electron ranging between 30 and 58 nanometers. So what they found decreased in set speed, but it's still comparable to the GST, like on the range of 80 nanoseconds. But they found a reduction of low, of 30% of reset currents, very low. Also the very nice cycling endurance, 10 to the 8 cycles. But there was also the problem with resistance drift, like coefficient 0.1, which is on the average of GST 225, which is also close to 0.1. So this is the one problem with such composition, but it maintains high resistance state, so amorphous state after 6 hours of baking at 100 degrees C, so very stable phase. So of course then after several years there were many projects and research on improvement of this so-called golden composition, and here some another research. In this case they used GST and they avoided with up to 45% of germanium into the matrix. So such GST where they also showed very high TC. Also this TC can be also improved by introduction of doping elements like carbon and nitrogen. If you introduce carbon up to 4%, you can increase the TC till 400 degrees C. This is very high value. And it also increases 10 years the stability of the reset state. This is the 208 degrees C. And for doped materials, it's like on the average of 210 degrees C. But again, the problem of resistant drift and set state. The reset current is on the average of 600 microamp, decrease in the reset current and endurance more than 10 to the same 7 cycles. From microstructural point of view, this is a very interesting material, because if you heat up it, you see it has a huge amount of germanium. If you heat up this material, you can observe the formation of different clusters of precipitates, like germanium rich, mostly germanium rich material. If you compare here, this is a lot of germanium, here is less. and this is also antimony telluride phase without some germanium. So there is here phase separation, but nevertheless these such devices can be operated till to the 10 to the 7 cycles. Now let us consider these concepts of composites. If you make GST, if you mix GST, some oxides like silicon oxide or titanium oxide. If we do like this, what happens with material? The material will form like germanium, GST grains, which are like dispersed in the CO2 or TOX matrix. So this brings to that the EC increases a lot for this SOX doping until to the 6.4 E volt for high doping. Also the resistivity of amorphous phase, it's also increases in the amorphous and in the cubic phase, but mainly in the crystalline phase. The high amount of SOX, you see the increase of till to order of magnitude. Here the resistivity of amorphous phase does not impact a lot. Interestingly also that such a composite, they improve the thermal conductivity of the overall system. So it in the sense that the overall thermal conductivity of amorphous and crystalline phases, they are both reducing. And also in the case of TOX, also the same effect that the thermal conductivity is reducing. Then reset current for such composites, it's also reducing a lot. Like you can see, this is for pure GST, this is for doped, for differently doped SOX, that the reset currents are much lower compared to the pure. So, and of course there is this increase of resistance of crystalline state, which is good for the reset operation. So here also some examples of alloy of composite making of germanium-rich alloy GST451 and silicon oxide. Here again, increase of crystallization temperature, increase of the data retention, and some tests on the device performance. Here they make like offset for cell. Here this is the one lower bottom contact. This is chalcogranite layer. This is the bottom contact. But they also introduced some resistor layer here to minimize the device heat loss. And they found the set time like 500 nanoseconds and 500 nanoseconds for reset. Stable endurance here. Reset current also low 177 microamp, and they also found the low reset current density, which is 4.1 MA per square centimeter. If you think for pure GST, this is on the average of 20 MA per square centimeter. Also another alloys like with another materials, carbon, silicon, carbon, they also act like they help to improve the reset current, and they reduce this reset current. Like if you consider reset current for pure GST, it's in this range 435 microamp. this is for composite, and the reset current density is also like in this on this range. So we see the reduction of reset current by materials and device engineering, and the next challenge comes from the mass production of such PCM devices. So now I think we can make a short break and then continue. If you have some questions, please ask me. Yeah, please. The microphone is there.
Professor, so basically when we talk about industry, so in circuits we do aging simulations to get to know the performance, like what we talk about the retention time. So how do we measure it here, the retention time? Like we saw that in nitrogen doping the retention time was an issue with the 2 years, and then we go back to oxygen and carbon doping. Likewise we move on to titanium doping. So how do we measure the retention time here?
How do we measure the retention time? Shivendra, maybe can you explain this?
Yes.
Because your device side.
Yeah. So for retention time, possibly you should test your device. First, you should understand what is the retention. Retention means how much time it can withstand our memory. So say suppose if we talk about here, so the retention of bits is more than 5 years, 10 years, something. They have tested. So how we can do this? You first program yourself, and then you leave that device for some particular moment, and then again you read that same voltage. So if it's retain that value, that particular time, so then you can say that yes, our material is well enough for retaining the memory. So this is the part of you need to characterize for multiple time. So if we are having a stable material, the way in the material aspect you have seen the stable phase we need to identify, then you can characterize it.
Okay, so how do we know that it will last for 10 years? So we'll, like you say, that you'll program and you check. So for 10 years, how do we know?
So for that,
simulations we need to carry out.
Simulation you can do that, but in that case you need to project this thing. Okay, you need to project for some kind of moment, and then you need to make some kind of a projection on that.
Okay.
Like earlier memories, which they have shown some kind of hypothesis kind of. Hypothetically, you have to understand. Okay, this can withstand up to that level. Okay. So for retention, you need to check that particular bit for a moment, and then you can have some kind of a projection that okay, in that time scale.
Just extrapolate it.
Yes, exactly. I mean, like in 10 years you cannot simply one device you can do, So if for some particular moment, a particular device you can say that okay, these bits are continuously retaining, then you can extrapolate the things and then you can identify.
Okay. Thank you.
Yes. Anything else? Yeah, you can. Live? Okay. Okay.
Sir, while doping or alloying is taking place, is there some challenges when the mixture are not mixing properly, something like?
Yeah, the process, if you make a doping, it's not only both your elements on sides where you want, and this is somehow the problem. And the problem also the phase separation, which can be induced by such doping.
And to improve the microstructure, what kind of what we can do during the heating process, like heating profile and all, what kind of things we can do to increase the microstructure?
In the case of doping, it's like self-defined process. So the grains form smaller. This is intrinsic properties of material. In the case of GST, this is the nucleation-dominated material. So you have many nucleation sites, and then the size will be in this range 10-20 nanometers. So you cannot do a lot by just heating or something like this. we don't introduce impurities or another elements to reduce the grain size.
Sir, in the nitrogen doping condition slide, we are discussing about since the grain size is small, the endurance is high. Endurance is getting high because of the grain size is small. We discussed like that, right?
Yes, yes.
How it is happening, like if in SCM we are finding that as a grain size is getting small, it is possible that we can predict the endurance will be higher.
Yes, since it's found experimentally that such if you have such small size, grain size, the endurance is getting better.
Okay. Experimentally, it is proven, right?
Any more questions? If not, then just we'll have a short break, not more than 5 minutes. Just be here, then we'll start in another 5 minutes. Okay, and then we'll wind up because in the second half we have our valedictory session and examination also. So we'll quickly start this another session, and then we'll close about this our lecture and tutorial part of this whole CAN course, so that we can discuss about the examination in the second half, and then finally valedictory ceremony. And one more announcement about this exam, just we have rescheduled half an hour before, so we'll start our exam 2:30, so that we will get half an hour time for valedictory session when the certificate distribution and all those things will take place. So be here, all of you, at 2:30 after this session in the second half, so that 1 hour exam we can take place here. Okay, so just so we'll start in another 2-3 minutes. Yeah. Okay, thank you.